Morning, everybody. Today we get the privilege and the awesome opportunity to talk about probability. So, probability is a big, wide topic, and you'll cover it for all 4 years you're in math, and you'll even cover it when you get to college. And probability is kind of a big part of mathematics as it stands. Today we get to talk about sets and Venn diagrams. So, in probability, a set is a collection of objects. It could be anything. It could be a collection of numbers, of letters, of people, of sports, of states, anything. If it's a collection of objects, we're going to call that guy or girl a set. And then each object within that set is called an element. A capital letter will be used to define the set or the elements listed within curly braces. And you guys know what curly braces are. They are those things that you said somehow only teachers can draw them, but you guys will too. So that is our curly brace. If a set has no elements, we call that an empty set. And you'll see that it could also be called a null set. You'll either see it as a 0 with the slash through it, or you'll see it as a set of empty curly braces. So let's go ahead and practice some sets. Now, if we look to the left here on our note sheet, we've got this little note. A finite set has a distinct and countable number of elements. So that's a finite set, distinct and countable, whereas an infinite set does not have a distinct number. So when we do these sets, we're going to determine whether or not they are finite or infinite. So the set of states beginning with the letter O. Now, I don't need you sitting here singing the 50 States song, so I'm going to help you out a little bit. So a set of states that begin with the letter O. So our set is going to be set O. Well, obviously it is one of the greatest letters in the alphabet, but also it's how we're going to be able to distinguish what we're doing. So for set O, we're going to pop in our curly braces, and then we have 3 states to start with the letter O. We have OH, IO, and then we have way over there in Oklahoma, if I can spell Oklahoma correctly. Remember, we are a math teacher and not a English or history teacher. And then our final state with O is the Nike capital, Oregon. So there are no more states that start with the letter O, so we're just going to stop right there. We're going to close our set with a curly brace. Now it goes back to that note on the left. Do we have a finite set or an infinite set? Well, because there are only 3 states that start with the letter O, this would be a finite set of data. Example 2, a set of prime numbers. We're going to capital P to help us identify this set. So prime numbers are any number that is divisible by itself in 1. So we've got 2, 3, 5, 7, 11, 13, 17, 19, and we can continue forever on these dadgum prime numbers because prime numbers will always keep going. That was an awful curly brace. Let me erase that real quick. So these prime numbers will continue forever and ever, and you see that listed with the ellipses. So this is an infinite set of data. And then our final one, set of multiples of 4 that are odd. Well, that seems like an odd question. So multiples of 4, what do we got? If we have just multiples of 4, we got 4, 8, 12, 16, 20. When we look at those sets, no matter what happens and no matter how we do it, there will never be a multiple of 4 that's an odd number. So this, ladies and gentlemen, is an empty set. Or you could say, oops, come on back to me. Or you could say set M is empty. Just some blank curly braces. Our next set we're going to come across is called our universal set. And a universal set contains all of the possible elements for a certain problem or solution, or problem or situation. The universal set, now hold on now, is denoted as the letter U. Whoa. Another fun word for set, another fun word that comes in our set language. Set A is a set of all elements in a universal set. So this would be the complement. So if we think back, we've heard this word before. If it's going to be a complement, it's going to be what's not within a set. So if it's not in set A, there's two ways we can denote this. So you could see it as A prime, or you could see a bar. You'll see it both ways, and they're just saying, hey, we want what is not in set A. So for example, we've got universal set U. It's got 1, 4, 7, 10, 12, 15, 17, and 20. And they give us set A, which is 4, 10, and 17. They want to know what is not in the universal, what is not in A, but is in our universal set. So the easiest way I'm going to show you guys how to do this, get your handy dandy highlighter. We got 4. Let's find 4 within our universal set. Okay, we've got 10. We'll find 10 in our universal set, and we've got 17. So if a number is not highlighted within our universal set, that means it is not in set A. So that would be curly brace 1, 7, 12, 15, and 20. So those are values that are in the universal set, but they are not in set A prime or A bar. Okay. Intersection of sets, where they cross. Sets A and B are sets of all elements that are both in A and in B. So when you see this, you'll see it denoted with almost a letter N. It looks like an N, but it's not. Okay, so it's, why did I put D? Oh, because I'm thinking in my head and. So A, and then this little symbol here, this little N looking guy, means and B. So it has to be a number that is in both A and in B. So again, we look. All right, get our handy dandy highlighter. So we go number 2. Is the number 2 in set B? Yes, it is. All right, good. How about 6? Is 6 in both? It is not. 10 is in both. 13 is not. 15 is not. But 17 is. So if we want an intersection, we want numbers that are in both A and B. So curly brace, we got 2, 10, and 17. That's a curly brace. And then last, one of our last things with sets is called a union. So a union is in A or B. So it makes a little U looking symbol in the middle, and it's just where A and B are A or in B. So A union B. So this means that if it's a data point, it can be in both sets. So now we've got to go through and we've got to take all possible numbers. So 2, 6, 10, 13, 15, and 17. So we know everything from A is going to be there. And then we've got 2, which has already been given because it's an A. 4, 10 is already there. 12, 17 is already there. And 20. Now, if you want to get really good, and we want to be really good, we need to put these guys in order, least to greatest. Oh, gosh, that was an awful curly. So 2, 4, 6, 8. 2, 4, 6, 10, 12, 13, 15, 17, and 20. And yes, that is the way it has to be done. Go ahead and erase that, and we'll move this rascal on down. Okay. So now we can visualize our sets with these things called Venn diagrams. Now, I'm sure you've seen Venn diagrams, but you might have thought them to be something else. In English, you know English, those jokers, they just take all kinds of things. But in mathematics, our Venn diagrams are going to help us display our sets. So in the diagrams below, we're going to shade to show the relationship, and then we're going to give the symbolic notation below. So for the first one, it's the complement. Remember, this is what's not in our subset. So A prime, or it would be A bar. And when we shade, we're going to shade everything that's not in the circle A. So we're going to shade all around it. Our second one is the intersection. So it's where A and B overlap. And remember, that's A and B. And that's just going to be this little piece right here in the middle. Only where A and B overlap. And then finally, we have our union. So it's where A or B. And look at that. I'm trying to write the actual letter or. So A or B. So it can be in A. So we're going to highlight all of A. And then it can also be in B. So we're going to highlight all of B. So those are 3 different ways we can visually see what's going on in our Venn diagram. So let's practice now with some different sets. So it's going to say U is our universal set. Whole numbers that are at most 8. So the highest they can be is 8. And then we have set A, which is 2, 4, 5, and 7. And set B, which is 1, 4, and 7. So if I look over here, and let's just use a little bit of our own little thing. So anything that can be at most 8. So 0, 1, 2, 3, 4, 5, 6, 7, and 8. So those are all the possible outcomes. That's the numbers in our universal set. So if I had a U, and then I do curly brace, those are all the possible numbers. But A and B have got their own little set of numbers that we've got to go ahead and calculate. So A has 2, 4, 5, and 7, and B has 1, 4, and 7. Now the sets have some similarities, so those similarities are going to go into our intersection. So 4 and 7 are in both, so it goes to our intersection, and we can erase them out of only set A, and we can erase them out of only set B. So if we only want A, we've got 2 and 5. If we only want B, we've got number 1. If we want A and B, we have 4 and 7. And then there are some numbers from our universal set that don't fall in A or B. And that would be 0, 3, 0, 2, 3, 4's in there, 5's in there, 6, 7's in there, and 8 is not. So 0, 3, 6, 8 are in our universal set, so they get to be in the box, but they are not in our set A or B, so they can't be in our circle. So we want numbers that are not in A. So anybody that's not in A would be any number in our universal set. So we got 0, 1, 3, 6, and 8. 0, 1, 3, 6, 8. The only numbers that can't be is 2, 5, 4, and 7. How about the guys that are not in B? So now we've got 0, 2, 3, 5, 6, and 8. So if I was shading, I could say it's all of these guys and all of those guys. If I was shading, that's what I would look like. In the intersection of A and B, remember this little guy means and. Get used to seeing this notation, guys. So that means and. So that would only be 4 and 7. And then lastly, in A or, again, learn our notation, A or B. So now it can be in either one. So 1, 2, 4, 5, 7. And then notice that does not include the ones that are out there. Okay, our last piece of sets are going to be called subsets. So a set is a subset of another if all of the elements are contained within another set. So B is a subset of A, and we would write it as B, and then this little sideways C-looking guy, A. So that would be B is inside of A. And that might be so that means all of the data of B is inside of A. So they're going to give us two sets, and they say, hey, determine whether or not one is a subset of the other. If yes, describe the relationship using the proper notation. That would be using our subset notation. So it says A, natural numbers less than 10. Remember, natural numbers are our counting numbers. So we look at set B, 2, 5, and 9. Well, those are counting numbers that are less than 10. So we'd say yes. And then our notation would be B is a subset of A. B is a subset of A. Hearts in a deck of cards. So you guys are going to have to get real used to deck of cards, but you got 4. You got a heart. I am not drawing well today. You got hearts, diamonds, clovers. That was a pretty good one. And spades. That was not a good one. My bad. That's awful. Okay, so there's 4 suits in a deck. And we want to know A is all the hearts. And then B is all the 4s. Well, this is not a subset because there's a 4 of diamonds, there's a 4 of clubs, and there's a 4 of spades. So this would, B would not be a subset. A, months in a year, and then B, months that begin with the letter J. Yeah. A is months in a year. That's all 12 of them. And then, of course, we have months that begin with the letter J. So June, July, January, great month. Right? So then we would say B is a subset of A, a little inside notation. And then multiples of 10 are multiples of 5. So let's check. So multiples of 10 would be 10, 20, 30, 40, etc. And then multiples of 5 are 5, 10, 15, 20, 25, 30. And that would continue forever. Well, if it's a multiple of 10, do multiples of 5 fall in? So yes, we would say yes. But now instead of B being inside of A, because not every multiple of 10 is a multiple of 5, we would say all multiples of 5, all multiples of 10 are within all the multiples of 5. All right, that completes our notes for today. Thank you guys for watching. Go be great.